Here we have the set n squared, so n times n, and n is the natural numbers. And we define this correspondence in this Cartesian product of n and n this way. So this pair is related to this pair if this relation holds. We have to prove that this is an equivalence class, okay? And then we have to find the equivalence classes of these numbers. And finally, we have to identify the quotient set n squared over this correspondence. And the interesting question which we're going to answer is if we can identify this quotient set with some number set. And that's the importance of this example. So here you have, well, let's do first the proof that this is an equivalence class. To do this, we are going to first write this relation in a clear way. So notice that if we put this here and this here, what we have is this relation. This is equivalent to that. So that means that two pairs are related if the difference between the first number and the second is the same integer number, right? Okay, then it's very easy to see that it's reflexive because mn is related to mn, right? Obviously, if you replace p and q by mn, you have an equality, an identity, right? It is symmetric because if mn is related to pq, that means that m minus n is p minus q, okay? Which is equivalent to saying that p minus q is equal to m minus n, which is equivalent to saying that pq is related to mn, okay? So it is symmetric. And finally, it is transitive because if mn is related to pq and pq is related to rt, okay, this means m minus n is equal to p minus q. This means p minus q is equal to r minus t. So if these two sides are equal, then these two sides are equal. So it means m minus n is equal to r minus t, which implies nn is related to rt. Okay, so that's the transitive property. So it's an equivalence. It's an equivalence relation, right? This is wrong, by the way. This is relation. Now we have to find the equivalence classes for these numbers. But first of all, we're going to show what the equivalence classes look like. Well, an equivalence class, right, is the set of all pairs PQ in N2 such that the difference P minus Q is equal to some integer. Okay, some integer. So actually, the whole class is identified by this integer here, right? So according to this, there are these equivalence classes. The first one is the class of the zero, which contains all pairs of the form nn, right, where n is a natural number. Okay, clearly these are all pairs whose difference is 0. So that's the class corresponding to 0, or k equal to 0, right? Then there is the class n plus r n, right, where n is any natural number and r is fixed. R is an integer, a natural number, sorry. R is a natural number, right? So these are all the pairs whose difference is equal to r, positive, right? And finally, you have here the last class, well, the last set of classes, which is this one, right? Which contains all pairs, right? Again, R is a natural number, contains all pairs for which the difference is negative R, so a negative number. And here you have all possibilities for K, right? K is 0, a positive number, or a negative number. So the classes are either like this, or like this, right? So this identifies all the classes. So now we need to see which one is the class of these numbers. Okay, the class of these numbers. This is, by the way, B, right? So let's begin with 1, 1. Well, 1, 1, of course, the difference is 0, so it belongs to the class, the first class, and N, where N is a natural number, right? That belongs to that. The second number, 2, 1, 2, 1 belongs to the class M plus 1 N, because the difference is 1, positive, right? Okay, so it's of this type, right? Then you have 3, 1. Okay, 3, 1, the difference is 2, so it belongs to this class. Okay, where N is a natural number, right? It's another class of this type. And then we have 1, 2, and 1, 3. Now 1, 2 is N plus 1, right? Because the difference is negative 1, right? So it's a class of this type. And 3 belongs to this class. Okay, again, a class of this type, corresponding to the negative number negative 2. Okay, and now the crucial question here, which is question C. If we can identify the quotient set, right, with some number set. And from what we've seen right now, it's clear that the number set we can identify the classes with is the integers, right? You see, every class, so remember the quotient set N2 over R, the quotient set is the set of equivalence classes. So you have is a set containing all these elements, and as you can see here, every one of these elements, every one of these classes is associated to just one integer, right? And the association is 1 to 1, okay? Actually, it's a bijection, right? There's to every class that corresponds just one integer, and to every integer that corresponds one and only one equivalence class, right? So there's a perfect identification of the classes, the equivalence classes of this set with the integers here, right? So this allows us to define the integers with only the natural numbers without reference to any sign, okay? So you see, we say that this number here is what we are going to call 0, but the definition, the description of 0 is done with natural numbers. So 1, 1 is first and 0, or 3, 3 is 0, right? Here is all the positive numbers, right? So 3, 1 is 2. It corresponds to 2, right? It's a positive number. And 1, 3 corresponds to negative 2. But again, these are natural numbers, as here. So the description of the integers, including the sign, is done with just natural numbers. No sign involved, right? And actually, not only that, we can also describe the operations in terms of these pairs. So we can say that M1 plus M2 is equal to N1 plus N2 plus N2. And let's see that this addition that we have defined here, which is perfectly natural, corresponds to the addition of integers. Let's see. Here, the integer describing this class would be this one, right? We make the difference. That is the integer that describes the elements of this class, these ones. And this would be the integer m2 minus n2, right? And this one here would correspond to the integer this. But of course, the sum of these two numbers is equal to this, right? So the addition of integers is perfectly well described with this addition of pairs that we have defined here. And not only that, we can also do the same with the product, okay? But the product has to be defined in this funny way. n1, m2, sorry, n1 times m2, n2 must be defined as m1 the product m1 m2 plus n1 n2, and then the second component is n1 m2 plus m1 n2, right? And again, we're going to see if this matches the expectations, right? So the integer here is m1 minus n1, and the integer here is m2 minus n2, right? If we multiply these two integers, we get a number. And let's see what we get here. If we translate this is the integer m1 m2 plus n1 n2 n2 minus n1 m2 minus m1 n2. Now if we multiply this number using the distributive property, what we have is this times this is m1 m2. Now this times this is minus m1 m2. This times this is minus n1 m2, and this times this is plus n1 n2. Now if you compare these two numbers, you will see that they are the same. So yes, this operation, even though it's a weird operation, it looks like a weird operation, nevertheless, this operation is exactly what we describe when we do the multiplication of integers, right? So the multiplication of this, the integer corresponding to this, by the integer corresponding to this, gives you the integer corresponding to this pair here. And the nice thing of doing this is that we are describing everything. We are describing the whole set and the operations involved using only the natural numbers and the standard operation of the natural numbers. We are just adding and multiplying natural numbers. No sign involved, right? So this is an interesting example that shows how using equivalence relations and equivalence classes, we can construct new kind of entities with new type of operations that reconstruct some of the number sets we already have, okay? Of course, this is something that we knew from the rational numbers, right? Because rational numbers are described as equivalence classes, right? So for instance, the rational number that we call 1/2 is not really the fraction 1/2. 1/2 is one of the fractions that describes this number. 2/4 is the other, is another, 3/6 is another, etc. There are infinitely many fractions, different fractions, right? Because they have different numbers describing the same rational number that we associate with 1/2, okay? Well, in the same way that we're using equivalence classes to construct the rational numbers, you see that we can do the same thing with the integers, right? We can construct the integers with equivalence classes with an equivalence relation defined just on natural numbers, on pairs of natural numbers, okay? And this example illustrates just that.